So we'll start with we stopped with connectedness last time. We'll do a bit of path connectedness, just a bit, and then we'll get into compactness. We didn't do path connectedness, and we're going to need that when we do homotopy. So I'll just introduce it a bit. So a path is a path connecting two points in a topological space is a continuous map going from the closed unit interval to topological space, such that it fixes the 2 points with P0 and P1. So P of 0 is fixed at X and P of 1 is Y, and that's your path. Now you can say a topological space is path connected if any 2 points in the topological space can be connected by a path. So that's your path and path connected property. Now we saw connectedness. Now path connectedness is basically it's kind of okay, I'm not going to say it's weaker, but yeah, just that any path connected space is going to be connected. This is the proof. The proof isn't that difficult. I'm not going to read through it because you can just read that. But yeah, the proposition is that any path connected space is connected. Then yeah, the converse isn't necessarily true. If you want to look for examples for the converse not being true, the counterexamples would be in metric spaces, right? They can be connected, but they don't have to be path connected. There are some examples. The last proposition is that just like in in connectedness, if you have a continuous map of topological spaces, then the image, the continuous image, is going to be connected to. So if you have two topological spaces and you have the subset of the space X, which is path connected, then its image in Y is going to be path connected to. And the proof is it's pretty easy to see. You just take two elements in the image and two elements in A. You have this condition. Now you use the path connected property to have a path, and then you take the composition of this F with the path that you just got from A, and this would give you a path which would connect X and Y. So thus F of A can be connected by paths. Okay, now we come to compactness. So compactness is another topological property like connectedness or path connectedness. And the definition, before going to the definition, we're going to define a few terminology. So if you have a family of subsets of a space, then it's going to be called a cover. If you take the union of all the family members, then it spans the whole space, right? So X is equal to the union of all the family members in that family. Now if you like make up this family by just taking open subsets, then your cover is going to be an open cover. So open cover is something we'll probably use a lot. Yeah. Now with cover, you also have something called a subcover. So a subcover of a cover is a subfamily which also spans the same space that the cover was spanning, right? So if you have a cover UI, then you have some subfamily UJ. So UJ is again like a subset of the family which is indexed by another subset, the original indexing set, right? and the condition is that subcover must cover the whole space as the parent cover did, right? So there's still a cover. And if your indexing set J is going to be a finite set, then the subcover is going to be a finite subcover. A finite subcover is going to be of quite importance to us when we go into paracompactness and essentially defining the whole manifolds. The definition of a manifold is going to depend on that. So anyways, we have a cover, we have a subcover. Then a topological space is going to be compact when every time you have open cover, you also get a finite subcover, right? So what it means is that if your space is compact, anytime you have a family of open sets that spans the whole space, then from there you also get a finite subcover. So another finite subfamily of open sets which also spans the space X, right? So that's the definition of compactness, compact spaces. Now you can define compactness in another way, namely through this finite intersection property or axiom, which is this. So if you have a family of sets as, then you say that this family has this finite intersection property if and only if for every finite sub-collection of this family, the intersection of the members in this subcollection is non-empty, right? So it's not equal to the null set, and that's your finite intersection property. Now how you can use that to define compactness, or essentially make a statement which would use this property, which would be equivalent to compactness. And this is what this proposition does. And I would encourage people to go through this proof right now. I'm not going to read through that. If there's anything that people can't understand, they can ask, and I'll be ready to explain. Oh, this should be an union, by the way. Yeah, the union is missing from here. Oh, wait, it should be union or intersection. Alright, so it's an intersection that is missing from there. So yeah, I'll maybe post this on the chalkboard. Go through this, and if there's anything you can't understand, we'll discuss. Otherwise, we'll move on. Why is it assumed that x minus bj is open? Because you're talking about x minus bj is open because we're taking vi as a family of closed subsets, right? So all of these x minus v's are going to be open. They're going to be complements, and the union of them is also going to be open. But by the way, you can like use microphone if you can, because kind of like keeping track of the chat is not, yeah. Okay.
Yeah, for the proof, what's the main idea behind the proof?
What is the main idea behind the proof you're asking?
Yeah.
The main idea behind the proof is that you just use this finite intersection property cleverly by choosing these family of closed subsets, and then it follows pretty much. There's nothing too much to think about it, but essentially you have to think about how to use this finite intersection property using these closed subsets.
In a way, the two definitions are complementary to each other, since the complement of open sets is closed.
Right.
So one definition is kind of gotten by taking the complement of the other definition.
Exactly. Yeah. Yeah. That's why it actually works. Otherwise, you'll have to do some more work. But yeah, just because like if you have like one of the things working, then you can just have the other thing by the complement. But yeah, I like this kind of formulation. I forgot it, like back when I did it, I forgot it, but like doing it again was nice. And from this, you can get a very nice corollary, which is that closed subsets of compact spaces, compact. Yeah. But the converse is not going to be true, and that but for that we'll need some other kind of condition, and that will be the Hausdorff condition. So this theorem is also pretty interesting. If you have a Hausdorff space, and if you have a compact subset of the Hausdorff, and you take a point in the complement of that complement with respect to that compact subset, then there exist disjoint open sets that would contain the compact subset and the point. And the proof is not that difficult too. What you do is you take a point in K, you use the Hausdorff condition, you say that, okay, there is going to be an open set containing Y, there's going to be another one containing X. Now all of these that contain Y, these UYs, are going to span K, right? And thus this is actually an open cover for K. and as it is an open cover, then you can take some of these actually m y's, then your K is going to be a subset of the union of the family members of this cover, right? Now you fix that with you say that this union is equal to U, then you say V is equal to the intersection of this kind of family. This is going to be open. This is a typo again, but yeah, this is open, containing X, and you get to sets U and V such that the intersection is now, and they contain the things that we want them to contain, the K and the X, right? So, yeah. And in this too, you get this corollary, which is very important in a lot of cases, that a compact subset of a Hausdorff space is closed, right? So this corollary is the converse of the corollary that we wanted, but you're not going to have it for general cases, so you need the Hausdorff condition. With the Hausdorff condition, you also have this interesting theorem, which is that if you have two topological spaces that are compact and Hausdorff, then if you have a continuous bijection between them, then it automatically becomes a homeomorphism between the topological spaces. Right? And the proof is not that hard to. You have to just show that the continuous bijection you have is actually a closed map. So closed map meaning maps closed subsets, closed sets into closed ones. So you take a closed subset of X. This is compact as X is Hausdorff. Now you say, okay, F, the image of A in Y is also compact, because, yeah. But your Y is Hausdorff too, so F of A is going to be closed from this corollary, and then of course get a closed image from a closed set, and you can do this for each subset A. Thus you have a closed map, getting the homeomorphism. Okay. There are actually a few more things that one can do with the Hausdorff plus compactness. These are the only important ones that I mentioned, but yeah. So we head over to preparing for the Heine-Borel theorem, which is kind of the important theorem to prove, but actually Heine-Borel itself isn't the goal, because once you do the Tikhonov theorem, Heine-Borel becomes just like a very special case of it in Rn. So the goal is Tikhonov, but the thing is we're not even going to hit Tikhonov because that's too hard to do, and it's going to take a lot of time than we have. So in the notes I've mentioned some places where you can look for it. Moncrief's Topology, as we talked about, it has that, and this MIT book also has a very interesting way to prove the Tikhonov using ultra filters. So you can check that too. But the version of Tikhonov that we're proving here is this one. That if you have X and Y as compact topological spaces, then their product, having the product topology, is also compact.
Sorry, can I interrupt you for a second? You mentioned that Heine-Borel is a special case of Tikhonov. How is that?
It's not a special case. It's more like the fact that if you have Tikhonov, then Heine-Borel just becomes the fact that you just take these compact intervals, and you have the product, and you use Tikhonov to say that their product is compact too, and then you're basically done saying that.
Oh, you proved one direction.
Right. Yeah.
I see. All right. Thank you.
Yeah. That's basically it. Of course, it's not directly from Tikhonov. I'm just saying that once you have Tikhonov, it basically becomes two-liner. Yeah. So this one that we're proving is just a case of two topological spaces, right? In this case too, I would like people to read the proof. I'm not going to read it. And if there's anything that they would like to ask, it probably should not be clear in the first reading. It wasn't to me. But if people have seen this before, probably they know it already. So yeah, go through this and see if there's anything you need to know. Post it on the chalkboard. Everyone good at the proof then? That's nice. Yeah, basically the main idea behind this is trying to find these W's, right? Once you've got these W's, you're pretty much done. So what we do, just saying the idea behind, is that you first see that your goal is to get these subsets like U cross V, right? So you take this point, you say, okay, so if you have a singleton with this whole space, that's going to be homomorphic to Y. That's going to be compact. And this is useful because if you have the singleton, you can have like a case for each point, right? So this leads to having these WX's, right? So for each X, you can have this thing, and together these WX's are going to cover all of X because they just contain these U's. And you say, okay, X is compact, we know that. So you're going to also get a free finite subcover which include these WX's. You're going to have this subcover, and you say, okay, now we can have finitely many sets from the open cover. Again, we're taking everything from the open cover that cover each of these WX cross Y. It is from here, right? There's a finite cover of W cross Y, so it's going to be covering WX cross Y. Now, if you make a family of these sets that cover each WX cross Y, then you get a finite subcover of A for this product space. So there's probably a very nice diagram for this in Moncrief's. Got to check. Probably it's Moncrief's. I'm not sure. Yeah, this one. Okay. Probably Moncrief does exactly this, but probably in a bit more. Yeah, few more words. Yeah, he does the finitely many yeah, he does like the more like one step ahead. Like we did it for two spaces, he does it for like finitely many spaces. And he uses the tube lemma, something that I didn't exactly explicitly mention, but it's kind of, the idea is the same. So here you have these W's, and for each W you get this strip, right? So this strip is the WX that we were talking about, and for each point X you can have a WX, and each of these WX is going to span the whole strip. And what you do, well, you say that together it's going to span X, right? So together for each point X you get W, so you have a lot of W's, and it's going to span the whole X. And this slice is also going to span Y. So that's kind of the intuitive idea. It's going to span X cross Y. Okay. Yeah, right. Yeah, that's what I was trying to do, to prove it for 2 and then use induction. I thought it would be easier, but I didn't really get into it. But I said, okay, we can do it for 2, so you can use induction, but I was just too lazy to do that. Moncrief probably does it using the tube because he needs it for his chapter 5, something like that. Yeah. Moncrief does this, and then in chapter 5, when it comes back to this, he's kind of using the same idea. But he'll have to reformulate it to include the zones lemma in some sense. But yeah, I agree that using what we did and applying induction can be better. Right. Yeah, that also could be true. He does the finite case, the easier one first, and then the general one. Yeah, that makes sense. Okay, so that was our week taken off. Now we get to Heine-Borel. For this, I haven't made notes, so I'll be referring to other notes to explain. But I don't know how many people have seen Heineborel before here. Like the proof itself.
I've seen it.
Mm-hmm.
Yeah.
I've
Does
seen
it have to
it.
do with something with? Yeah. Does it have to do? What that's the one with the sequential compactness is equivalent to compactness in metric spaces or something like that?
That's the Bolzano-Weierstrass theorem. It's kind of related to Heineborel, but not exactly. Like the Heineborel just says that if you have a closed bounded subset of Rn with the Euclidean topology, then that's going to be compact, right? Yep. Yes. Okay. Yeah. There's an if and only if. Probably. Let me check too. I think the last time I saw Heineborel, it was in the way he mentioned. But yeah, okay, so this is probably the one that Gauss is talking about. Yeah. If we have a subset of Rn with standard topology, then A is compact if and only if A is closed and bounded. Okay, yes. About it. Yes. I guess that's the one, isn't it? Yeah. So, wait a second. If I try to... Yep. So, this theorem assumes that Tikhonov is true, at least for case 2. Or maybe it assumes that it's true in general, the Tikhonov. And then it proves the Heineborel that we were talking about. It uses... Yeah, he says that it's a corollary of the Tikhonov. But, okay, let's try to go through this. And we'll be done with compactness. We'll go to paracompactness. This is a statement which says that a subset of Rn is compact if and only if it is closed and bounded. Okay, so so you consider the forward direction. So you take a K as a subset of Rn which is compact. Now, as you're living in Rn, you're going to consider open balls. Open balls under Euclidean topology. So, the cover of K consisting of open balls centered at the origin of all possible radii must have finite subcover. So the cover of K would be the union of these open balls that are centered at the origin of all possible radii. Okay, and like because it is compact, so this cover consisting of these open balls of being at the origin has a finite subcover, and that makes it bounded because you have a finite subcover. As Rn is Hausdorff, luckily, and all compact subsets of a Hausdorff space must be closed, K is closed too. So that works out. Now for the other direction, you use the Tikhonov, as I said before. You say that, okay, so this subset is closed and bounded. As K is bounded, the projection of K onto the ith coordinate is bounded too, right? So for example, you take for each I there is an interval, the closed interval from AI to BI, containing the projection of K. So this is the projection of K. Then K is going to be the subset of this product space. Okay? So you're taking n products of these closed intervals. Now each of these closed intervals is compact, right? Now Tikhonov, as we said, says that product of compact spaces is compact. So this product itself is going to be compact, and as we proved previously, any closed subset of a compact space is compact. K is compact too. So essentially, Heine-Borel becomes very easy once you have done the Tikhonov. So yeah. All forms of finite dimensional real vector space induce the same topology. Yes. Yes, right, yeah. So that was about compactness, and we made it until Heine-Borel. I did not get into sequential compactness, which is another interesting thing, and the theorem I mentioned, the Bolzano-Weierstrass theorem, which says that every compact metric space is sequentially compact, is actually an interesting thing. So the Oxford notes that I've got people into, it has those things, so you can check it out. Okay. So
is this
yep.
R infinity Hausdorff space?
R infinity?
Yeah, like
Yeah.
you
Yeah.
talking about. I don't. So, what is it?
Wait. It should be Hausdorff.
Yeah, I think it will. Yeah.
Yeah, if you mean Rn with the infinity norm, then it's a metric space and hence Hausdorff. If you mean Rn is the product of Hausdorff spaces, which I think is Hausdorff. Yep. Yeah, I think he was meaning it in the R infinity, like the R omega sense. Product of Hausdorff spaces. Okay. So yeah, let's talk a bit about paracompactness, and then we'll get into quotient spaces. So for paracompactness, we'll need some new terminology, something called refinement. So a cover of a space is a refinement of another cover if for each family member in the cover, anything in the cover, there is something else, U alpha, such that it's a subset. So V beta is a subset of U alpha, right? So it's not exactly a subcover because it can be confusing to think about a subcover as kind of like each of the things in the subcover is a subset of the cover. But in the subcover, we had the condition that it spans the whole space. Here, refinement doesn't do that. It's just kind of like a refinement of the cover. But yeah, so that's your refinement. There are other kinds of refinement. For example, a cover is said to be a star refinement of a cover if for each point in the space there is some U alpha such that X star is in U alpha, where X star is, of course, the star of X with respect to this family, and is the union of all the sets B beta of which X is an element. So essentially, we don't need the star refinement thing. We're fine with just refinement. But what we need for the paracompact definition is basically that a space is paracompact if every open cover has an open locally finite refinement. Okay? So every open cover that you have is going to need an open locally finite. So it's finite, but it's locally finite, but it's going to be refinement of that cover. I'm probably looking for a better definition that I saw elsewhere, because this book is kind of messy with all the things it introduces. Meta compactness, and all those things that we don't need. But Okay. So what do we mean by something to be locally finite? Well, if you have a topological space, a collection of subsets of X is said to be locally finite if every point of X has a neighborhood that intersects only finitely many elements of that collection, right? So that's a locally finite thing. And there's the whole big thing of metrization, which we don't get into because we don't need. But yeah, this is your definition of paracompactness. Every open covering has a locally finite open refinement that covers X. Yeah. The example that Moncrief gives is that of Rn. So Rn is paracompact. You take this open covering of X. Okay. So you have the same open balls of radius m centered at the origin. So for a specific radius, you choose finitely many elements of the covering that cover the okay, wait. Right, so you get this collection of open sets, then you take the union, and this union becomes the refinement of the covering, and it is locally finite, okay, because it intersects only finitely many elements of this refinement, and your refinement covers the whole space. Yeah. But yeah, so this is the paracompactness which we're going to need when we define what a manifold is. And this important theorem is that every paracompact Hausdorff space is normal, right? The separation axioms again. And the proof isn't that difficult to go through, but not something exactly we need. Okay, I am looking to just end compactness here. Anything that anyone would like to ask or say about compactness before we move on to quotient spaces?
It's not a question, but I think it's good to point out that products of paracompact spaces don't have to be paracompact, and just talk about products of paracompact spaces generally.
Yeah, that's an important thing. Product of paracompact spaces doesn't have to be paracompact.
Yeah, I believe the theorem is that the product of a paracompact space and the compact space is paracompact, but yeah, that's it.
Other than partitions of unity, does anybody know why we care about paracompactness? In this context?
I believe it's going to be like there's like Yeah, the partitions of unity is where you see it, but I'm not sure if there's anything else. I don't think so.
We'll find out as we go along.
Maybe. Or maybe we'll not find out at all.
I believe it's just partitions of unity, at least in more simple differential geometry. No, I'm not sure.
With regards to metrization, I guess there are some kind of like theorems that need paracompactness. For example, a CW complex, if you remember anything from algebraic topology, CW complex is paracompact.
Is there much to metrization theorems besides the famous complicated name with N and S theorem? Does the completely classifying one space is metrizable if and only if it's sigma locally finite and regular Hausdorff? Is there anything else to it?
I haven't read much of metrization beyond Moncrief's, so I can't really say. But that big classification theorem was all that I saw too. Maybe there is actually. I'm not sure. There are some there's this thing called the Smirnov metrization theorem or something like that. She goes along the lines of a space is metrizable if and only if it is paracompact, Hausdorff, and locally metrizable. I'm not sure if it's something I remember. Okay. Yeah, the product of paracompact and compact space is compact. Sorry, is paracompact. And the theorem is probably like a variation of, not a variation, but totally different from the Tikhonov. Okay.
Munkers gives that as an exercise, and his hint is to use the tube lemma.
Which one?
To prove that the product of a paracompact and a compact space is paracompact. Problem 2 there, exercise 2.
Okay. I think you can like have kind of the same approach as we did, but you'll have to riddle with a few things. I probably remember doing this, but it's been a long time. I don't remember the actual proof. Yeah. Yeah, this was the... Okay, so it is in the Moncrief, right? So this Smirnov metrization thing. Moncrief spends like 2 chapters just on metrizability and stuff. Anyways, let's get on to quotient spaces. So we'll do quotient spaces for some time today, and then tomorrow we'll go into homotopy theory, basic homotopy theory. I'll probably go into the fundamental group of the circle, and some definitions of homology. Okay. So quotient spaces. So we did product. We saw product spaces, right? So something analogous is the quotient topology of the quotient space. And the thing that should come to mind when doing quotient spaces is a way of gluing things geometrically. So through the notes that I'm going through, we have an example of X as this union of two Cartesian products of intervals. Right? So you have the unit interval 2 self, and you have 2, 3 with the unit interval. And so the idea is that you have kind of a relation. So in these notes, they're talking about a relation as like something more abstract than an equivalence relation. So equivalence relation is a special kind of relation. Here is just a relation between two things. So the relation is like joining each of the elements, each of the points, and you have some kind of like relation in the like larger context, right? So yeah, so we need an equivalence relation on X, which will give us an equivalence class, just like we do equivalence relations in like group theory and other areas. Probably everyone knows what a relation is. It's just taking two things and having a way of like operating on those two things, right? So if you have an ordered pair, and if you have a relation between them, then you write X, R, Y. Relation, a specific kind of relation is the equivalence relation, which is reflexive, symmetric, and transitive. So, reflexive in the sense X, R, X is equal to just X. So that's a reflexive. Symmetric says that you can change the order of things, so X, R, Y is equal to Y or X. And transitive is basically the associative condition. X, R, Y with Y, R, Z says X, R, Z. With each equivalence relation, you get something called an equivalence class. So the equivalence class is like partitioning things into putting them into like their relations. Like, so it's like each equivalence class contains all the things that are equivalent to each other with respect to that relation. And the set of equivalence classes is denoted by in this manner. So this is X mod R. Normally it's just X mod tilde. So tilde is the usual way of denoting relations. So essentially it's just modding the whole space by this relation. So what you get is like these equivalence classes that are partitioned because of this equivalence relation. And this gives you the quotient space, right? Okay. So how do you define an equivalence relation on a topological space? And so this is what this proposition 3.3 does. So if you have a topological space XD and you have an equivalence relation on X, Now you have this family T tilde, so you probably can't see the tilde, but if I zoom in, there's a tilde on top of T and U. So this is a family of subsets of U tilde in this equivalence set of equivalent sets. So this is your quotient space, such that the pre-image of each of these subsets is open. Okay? So it's in the topology. So these subsets together, they make up a topology for the quotient space. This is the quotient topology. So this is not exactly how you talk about quotient topology, but this I kind of like this way of talking about it. So first you take this these subsets such that their pre-image is open in X, and now these subsets, this family of subsets, generate the topology on the quotient space, and we call that the quotient topology. And to prove that this is actually a topology, you just have to go through the 3 axioms of the topology, right? That the null and the whole space are in the topology, and the arbitrary unions and the finite intersections are there. With the quotient topology, as we said, you get an inherent equivalence relation. So what this equivalence relation does, it helps us identify things, right? So if you have an equivalence relation between 2 points in a topological space, they become identical with respect to this equivalence relation. Okay, everything makes sense. Oh, I didn't see that question until now. Does the Tikhonov theorem work no matter how we define the product topology? I mean, product topology is just defined one manner. Are you talking about if you can have Tikhonov over box topology? I mean, if you just have the usual product topology, Tikhonov works. Okay, so continuing with our quotient topology, this proposition says that if you have subset in your quotient space endowed having the quotient topology, then this subset is going to be closed if and only if the pre-image of this thing is closed in X. Right? And this is a one-liner. There's nothing really to see here, but what you consider is the pre-image of the complement of this v tilde. So you have X mod R minus v tilde. You take the pre-image of that, and that is equivalent to X mod pre-image of v tilde. And pre-image of v tilde, if that is closed, then this thing is open. And if this thing is open, this whole thing is open, which means v tilde is going to be closed, right? So, you have that direction in both directions. So you have the relation in both directions. Okay. So there's this good example of how you can turn the unit interval into a circle, right, with some equivalence relation. We have this unit interval with the standard topology on R. We define the equivalence relation R on this unit interval by this following rule. So we say that for each x in the open unit interval, the singleton x is an equivalence class. Okay? So for each point in the open interval, it itself is an equivalence class. And then you say the set 0, 1 is an equivalence class in itself. So that's a separate equivalence class. So what we do, well, we say that, okay, if 0, 1 is an equivalence class, what does that mean? Well, that means that 0 and 1 are identified. They're identical with respect to this equivalence relation that we just defined. So 0 and 1 are one and the same under this relation. Okay? So they're identified, and thus what you can do is you can just glue these 2 points together. And intuitively, as you can see, if you just join 2 ends of a line, it's going to be a circle, and that's what we have. The quotient space is going to be homeomorphic to circle. But the formal proof is going to need a bit more work, because you're going to have these mappings well defined, make sure things are homomorphic. Okay? And this proposition 3.9 helps us do that. And example 3.10 it finally gets us the homomorphism between the unit interval, the closed unit interval under this relation with the circle. So I would encourage people to go through this proof of the proposition 3.9 right now and the example. And it's not hard to go through and see if there's anything they would like to ask. Again, I would put this on the chalkboard so you can check. Everyone is good with that construction, with that specific map they made, the F, which maps point in the closed interval to cosine 2 pi t, sine 2 pi t. Can someone say me like why they chose that map specifically? Yep, the parametrization of the circle, exactly. And this is tomorrow when we do homotopy theory. And if I go into the covering spaces and the fundamental group of the circle, we're going to use this map again. And it is pretty useful. But yeah, so everyone is good with this construction, because yeah, this is like probably the first step in making things homomorphic using the quotient topology. Okay. So we probably won't see it in these nodes, but back when we did topology on the server, we did gluing when we started homotopy theory. That kind of made sense, but I want to go back a bit and give you a much more rigorous definition of what a quotient topology is. So if you have a topological space and you have surjective map, right? So you have F from X to A, which is a surjective map. Then the quotient topology on this A is defined by declaring a subset of A to be open if and only if its pre-image is open in X, right? So as you can see, this is exactly what we said when we were talking about the quotient topology here, right? But except we did that with relation with regards to this equivalence relation, right? But here that's not necessarily the case. So yeah, this is just another definition. And quotient map is going to be a map which is surjective, and U in the codomain Y is going to be open if and only if its pre-image is open. So this is something people confuse when they see this for the first time with the continuous definition of the continuous map, and they're different. And yeah. So yeah, that's your quotient topology and the quotient map. This is the example of the circle being identified with the closed unit interval again. And this is another example of having the wedge of n circles. So the wedge of circles is essentially the circles attached exactly at one point. But if you increase the number of circles attaching to a single point, then you're going to have something like this. And if people who have taken algebraic topology or just homotopy theory know that the fundamental group of the wedge of two circles is the Z cross Z. So the ordered pair. So like for each time you complete going from one circle, so you start from this point in the middle, you go through this circle, and then you go through this circle. That constitutes one ordered pair in your Z cross Z. Right? Essentially, this means that you have like two sets of winding numbers. Okay, like this is all terminology that's going to be defined tomorrow. Yeah, just saying how quotient topology is helpful. Okay, there can be other examples of quotient topology being applied. We'll see the torus and the Klein Bottle happening here. So Gauss asks, wouldn't it be the free group on two elements and not the free abelian group on two elements? I think it would be the free abelian group. You need the commutativity. say you go around the second loop of the wedge circles clockwise, and then around the first loop anti-clockwise, and say you go first around the first loop anti-clockwise and then second clockwise. Wouldn't these two be distinct? Yeah, but like you're taking a abelian group of z cross z, so you can have like negative numbers. It doesn't negative, like a negative winding number would mean you go in the opposite direction. Is not abelian. Okay. I believe so. That's what pretty much what I was saying, that if you have z, then you're going to have winding numbers. It is abelian, yeah, it is abelian. That's for sure. I remember that. The reasoning I'm kind of forgetting. Okay, so if we're going to talk about it, okay, let's just talk a bit about it. So this is where we did it. So we need the fundamental group of the wedge is going to be the fundamental group of circle. This is the free product. So you have z, z. But you do have the abelian condition because both yeah, because it doesn't matter, because you're still in the integers, right? And the integers are commutative over negative. So like if you have like a clockwise loop in here and then an anti-clockwise here and then anti-clockwise here and then a clockwise here, they're the same, because the when you lift the loops, again I'm talking about the what is it, the covering. When you lift the loops, you're going to get the same things. But I think in detail you'll have to use the Van Compen theorem. You'll have to look at the this normal subgroup which you're modding out, and this will give you the So, I mean, I'm not sure if we want to talk about it, but Moncrief does have a whole section devoted to the wedges. Yeah, you have the free group, but like you have the like commutative condition too. That's for sure.
Sorry, are you saying that the fundamental group is abelian?
It is.
It is not? Just the reference. I think it's not. You can look at my example. For it to be abelian, it would mean that these two paths are path homotopic, but they are not. You can like once going in one direction, once going in the other. The inverses of each other.
God. Or am I confusing myself with the fundamental group of the torus?
I think we might be talking about two different things. Confusing the homology group with the homotopy group.
No, yeah. So what happened? I know a tiny little bit of homology theory, and I know that the first homology group is the abelianization of the first homotopy group. But in my mind, I just see Z O plus Z, and I think, oh, that's the abelianization. The abelianization of that is Z O plus Z because it's abelian. It was a very stupid mistake, but that's just what happened. I just kind of mixed up what the app is. So I confused that H1 app is pi1. Of course, it's the other way around, but I accidentally thought it's like that, or just at least computed it the way when looking it up. Because I just didn't notice that they have a homotopy section on there. But no, yeah, it's the free group in two elements. It's not abelian.
Right. Okay. Yeah. I agree. Yeah. I confused probably myself.
Yeah, the torus is Z squared. Not this.
Abelian, right?
Yeah, the torus is the abelian free group in two elements.
Yeah. Okay. I confused. Right. Yeah. The thing is, the torus has the skeleton of the wedge, so I probably just missed the skeleton and equated them. Yeah. But yeah, stuff. And good stuff coming up. Let's see what else we can do. This proposition says that if you have a surjective continuous map between topological spaces, you have an equivalence relation, and if X is compact and Y is Hausdorff, then the quotient space and Y are homeomorphic. That would be pretty intuitive, I guess. But yeah. So we'll try to see how we can do the torus. So in this example, if you consider the closed planar unit disk, so you have the unit disk on R2. This is your D2, and this is your disk, and you have this following relation, equivalence relation, which says that okay, all the singletons in the open disk are identified if x squared plus y squared is less than 1. So for all the x and y's which satisfy this, they go into this class. And the boundary circle S1 is an equivalence class itself. So you have these two classes. Then the quotient space D2 mod this relation is homeomorphic to the two-dimensional sphere. And the way you prove this is by having a map between the disk to the sphere and using what we proved in this proposition, using the compact and the Hausdorff conditions. Okay. So this is your map F. So it takes xy from the unit disk and it maps it onto this. And this, like, just by looking at it, it looks like something that would be in the circle. But yeah. So how you can like try to do the torus graphically? Well, graphically it's pretty easy. If you have like a paper, like a rectangular paper, a square paper, right? And what you do is like you try to identify the bottom and the top edges to the left and the right edges. So it's like first you identify this left edge to the right edge, and that like becomes cylinder, right cylinder, and then hollow cylinder. Then you identify the top and the bottom. So that gives you a torus. Oh, you're talking about this map that we have here, F?
Yes, yes.
Okay, so for that you have to basically use this condition. So for example, you have this x squared plus y squared less than 1, and you have these conditions. So you use the map that we saw before, this cosine 2 pi t. But like instead of t, you're going to have square root of x squared plus y squared, right? See that?
Yeah.
And for each of the variables, you need x over root of x squared plus y squared so that you can get the length right. But yeah, this is just the typical parameterization.
So, like, can we derive it using some analogy with the stereographic projection map?
Yeah, that's a very nice point. And it's probably going to be in the problem set or something like that. But yeah, with the stereographic projection, you can do something like that.
If I had to make a guess, it would be like the composition of identifying the interior of the disk with the entire plane combined with stereographic projection or something like that.
Yeah.
Yeah. Yeah, I think that would.
I remember we probably did this too. Yeah, I'm like reluctant to get too much into this because we'll need fundamental groups which we haven't seen. But this is cool stuff. Wait, it's not this one. Yeah, this was probably for the triviality of the fundamental group of Sn. If n is greater than or equal to 2, we use the stereographic projection. But yeah. Okay, so yeah, that's pretty much that. So let's see. How you do a Klein Bottle? Well, Klein Bottle is something similar. We'll have to consider these. So for the Klein Bottle, you're going to have the unit interval cross the unit interval mod this relation, and this relation is defined by identifying x0 with x1 and 0 y with 1, 1 minus y. So if you try to think about this, like in the first identification, you fix the x and you say, okay, so 0 and 1 are the same. Okay, this is kind of like the how we did it with this like interval and the circle. And then you say, okay, so if you have at 0 you have y, 0y is identified with 1 comma 1 minus y. So 1 comma 1 minus y is like for the opposite direction, doing in the opposite direction. And the proof of like getting this is like going to use the fundamental group and all of that we haven't seen, but the construction as the quotient is this. And then you also have something called the projective plane, which we didn't see. The projective plane is got by identifying the antipodes of the sphere, right? So what you do is you have a sphere of like dimension 2, and you identify each point with its exact opposites, the antipodal point, right, minus x. And you do this for each point x, and you're going to get something which is not sphere at all, but you're going to get something called the real projective plane. And this is a very interesting thing, actually. When we were doing this course, we spent like around 2 lectures just talking about the RP, and there are a few interesting things about it, which we probably will see later, but yeah. And similarly, you can do the Mobius band, the Mobius strip. I think for the Mobius strip, we also have it. Yep. So right, yeah, that's what I was like going to say, but I stopped because I probably thought it would not make sense because we're just talking about graphically. But yeah, the real projective space is by identifying lines to the origin in the punctured RN. So, like for example, if you have RP 2, right? So RP2 is going to be your graph, like with the punctured origin, and you have like lines coming out of the origin, and you identify each of them. Okay, so we'll see this Mobius band as the last thing, and then we'll end today's session. So Mobius band is also got from having some kind of equivalence relation on the Cartesian product of the unit interval, right? And that is, so this is actually a very, I think I'll post this, but this part of the course is basically, if you have this x, which is the unit interval with itself, you have four kinds of things, right? So A is the singleton 0 with the unit interval. A prime is the singleton 1 with the unit interval, and B and B prime are the same thing in the opposite order, right? And what you do is like when you consider to create surfaces, you glue each of these A to B prime, or you just play with these four spaces, right? So cylinder you get by gluing A to A prime using this equivalence relation, right? For the Mobius strip, you have the equivalence relation of 0t with 1 comma minus t. So like how you kind of think about this is you have like a sheet of paper, right? You identify like 0 with 1 and t with 1 minus t. So 0 with 1 is okay, just like we did the like unit interval connecting its ends. But 1 minus t says you like invert it, you invert it while you're connecting it, right? So this is the reason why the Mobius strip, when you like connect it, you invert it, because you're having the equivalence relation with 1 minus t. So that's your Mobius strip. I'll post these on the chalkboard for later reference. You can check it on the Topology channel. If you go there, these lecture notes are still there. Describe the points in the punctured unit disk in polar coordinates r theta, right? And P is equal to I star r. Okay, and then plug into the standard parameterization of the circle. Okay, yeah. So that was about creating new spaces, quotients, and we did some compactness stuff. Next class, so that will be the last class before we are done with topology and we go into manifolds. I will try to do as much as I can of homotopy, homology, and a bit of these, more of these kind of like surfaces joining kind of things, right? With the maths, of course, because we're going to need these handles, cross caps, and all of that. We're going to need it, but I'll try how much we can cover. Okay, sure, yeah. Yeah, thanks for mentioning it. So you go to the intro topology, you go to end messages. You'll have to scroll a bit. Yeah, these notes. These are the Myers-Beckham. Yeah. I'll put the link in the chalkboard. But so that was like back in March, April. We were doing topology. Yeah, so this is not the MIT course actually. This is on Harvard's Math 131 course. Yeah, it was a very recent course, so that was helpful. But it was following Moncrief's for the first half and Hatcher for the second half. So the second half of the course was basically introduction to homotopy theory from Hatcher's chapter 0, something of that level. So yeah, it was pretty good. Okay, so we'll meet tomorrow. We'll meet Friday. Sorry, Friday at the same time. We'll continue our stuff. And Friday I'll post the P set, which for all these things, and it will be due on next Friday. 3. It will be due on next Friday, yes, for PISA discussion. So, yeah, I hope this was helpful.
Great job. Thanks a lot.
Mm-hmm, mm-hmm.
Thank you.
Yep. See ya Friday.